Today we're going to explore the TCS34725 RGB sensor for Arduino, and we're going to come up with a couple of simple projects. I'm also going to post some videos showing how fun this sensor can be and how useful it is in such a wide range of Arduino projects. And if you haven't used it yet, I think you're going to like it. Today we'll be using the Arduino Uno R3, the TCS34725 RGB sensor, two half-size breadboards, some jumper wires, the HW201 IR sensor. The TCS34725 is a color sensor capable of detecting and distinguishing different colors. It integrates RGB and clear light sensing elements to provide accurate color readings. It's known for its sensitivity and wide dynamic range for accurate color detection. You'll notice on the datasheet it says that it has an onboard IR blocking filter for clear color differentiation, and you may wonder what that is. This filter blocks most of the infrared light from reaching the sensor, and as you know, infrared light is not visible to the human eye but can be detected by the sensor, and without the IR blocking filter, the infrared light could interfere with the sensor's ability to accurately detect and differentiate between visible colors. So this is useful for more precise readings in environments with strong IR sources like sunlight, which could otherwise skew the color readings. You'll also notice that there's an onboard LED that provides consistent and controlled illumination for the object being measured. This consistency is crucial for accurate color detection, as variations in ambient light can affect the sensor's readings. This sensor has 7 pins. The one on the far left is the LED pin, and we use that pin to control the onboard LED, which you'll see in this video. The next pin is the interrupt pin, and this is optional for applications requiring interrupt handling. The next 2 pins are the I2C communication pins. The SDA is the data pin, and the SCL is the clock pin. The next pin is the 3V3 pin. This sensor has an operating voltage of 3 volts with a maximum of 3.8 volts, and will provide power to this pin from the Arduino 3.3 volt pin. The next pin is the VIN pin, and if you flip it over on the back, you can see that it accepts 3.3 volt to 5 volt. The sensor includes an onboard voltage regulator that takes the input from the VIN pin and it regulates it down to 3.3 volt, which is the operating voltage required by the sensor. While it is okay to apply 5 volts at the VIN pin, do not apply 5 volts at the 3V3 pin. On the back it says logic 5 volt safe. This means that the sensor's input-output pins, or the SDA and SCL pins, are tolerant to 5 volt logic levels, even though the sensor itself operates at a lower voltage. Our first setup will simply be to connect the I2C pins to the Arduino, and we'll do that by connecting SDA and SCL to the SDA and SCL pins, and the ground and the 3 volt pins to Arduino as well. Here's the code that we'll be using today, and you'll notice we have 2 libraries, the wire.h library and the Adafruit library. If you don't have the Adafruit library, go to the library tab over here and just type that in. You can download the library right here, and then once you get that set up, you click library tab again, and these libraries are important for I2C communication. This is where you go to select your board. Make sure you have the proper board. I'm using Arduino Uno. If you're using a Mega or whatever, you type in that. So let's type in Arduino Uno here. There we go. You want to select that. And also on the right side here, if it were connected, you'd see ports, and you select the correct port. And down here at line 5, we create an instance for the color sensor with specific integration time and gain settings. And in the setup, we set the baud rate at 9600. And the I2C communication has its own clock speed, and it's typically set by the hardware in the libraries, and it doesn't need to be specified in the sketch. So the baud rate we set here is specifically for serial communication between the Arduino board and the computer's serial monitor, and it's unrelated to the I2C communication happening with the sensor. Also in the setup, the sketch attempts to initialize the color sensor, and if the sensor is found, it'll print the confirmation message. Otherwise, it prints an error message and halts the program. Now, the loop runs repeatedly, and this declares variables to store raw color data, which is red, green, blue, and clear, and it reads that raw color data from the sensor. Here down here at line 23, we check and process the data. It checks if the clear channel value is above a threshold to determine if there's a significant color detected, and then if so, it'll print that color data to the serial monitor. This is where we calculate and print color information. It calculates the color, temperature, and luminosity, and then it prints the color, temperature, and lux values to the serial monitor. And if you're asking yourself, what is a lux value? Well, this measures the amount of luminous flux per unit as perceived by the human eye. It just indicates how bright or intense the light is or appears to be at a specific point. And finally, the sketch determines the dominant color by comparing normalized red, green, and blue values, and it prints that to the serial monitor. And then finally, we have a delay of 2 seconds at the end. Alright, we're going to go ahead and plug in the Arduino. We're going to go ahead and make sure we have the correct board selected and port, and click upload. Then we're going to expand this bottom window so you can see the serial monitor. Click on serial monitor, and now we get readings, and we get readings every 2 seconds, and the LED just stays on, and whatever color that it detects, it prints to the serial monitor. So I can hold up this Lego here, and it should print blue, and it'll continually print. And I'll hold up this green one, it should print green, and it's green. So this would be for continuous scanning where the LED is left on, but I don't want that. I want the LED to come on only when there's an object to scan. So only if something's in proximity. So let's set it up that way. For this next setup, we're going to go ahead and introduce the HW201 infrared obstacle avoidance sensor. This is designed for detecting objects and obstacles. The sensor can detect objects at distances ranging from 2 centimeters to 30 centimeters, and it can be adjusted using this onboard potentiometer. It has an operating voltage of 3.3 volt to 5 volt, which works out pretty well. So we'll go ahead and connect it to our 3.3 volt breadboard rail. It also consumes approximately 20 milliamp supply current, so this works out pretty well for what we want to do. As you can see, we made a few changes. We now connected the LED pin of the collar sensor to pin 9 of the Arduino. We've connected the VCC and ground pin of the IR sensor to our 3.3 volt breadboard rails. And we connected the output pin of the IR sensor to pin 10 of the Arduino. We've altered the code a little bit. We've added an IR pin at pin 10, an LED pin at pin 9, and we introduced a Boolean flag to track object detection. In the setup, we set the pin modes for the IR sensor and the LED to ensure that the LED is off initially, and this turns off the LED on our collar sensor. In the loop, the sketch reads the IR sensor value and checks if an object is detected. And this modified sketch only takes color readings when the object is detected, and it also handles turning on and off the LED. And this turns off the LED after taking the color reading, and this resets the object detected flag when no object is detected. Now it's time to plug in the Arduino and upload it just as we did before. And I wanted to include this part just in case you may have a similar issue with trying to get it to scan the correct color. If you scan something that's red, like this Lego here, and it comes up green or another color, you may have an issue with too much light directly on the sensor. I'm using a lamp here, and also, for me, it was an issue of it scanning before I had the object directly over the sensor, as you can see here. So it comes up a different color. So let's fix that by adding a delay. And so we'll go back to the sketch just after the object is detected and add a delay of 1 second. And this should give me time to have the object situated over the sensor so they can actually do a reading. Okay, we've uploaded this sketch with the added delay, and you'll see that when the IR sensor detects this Lego, it gives me just a second before it starts scanning rather than scanning immediately. And the color is much more accurate. So if that's one of the issues you're having, maybe a delay will help. You also don't want to have light shining directly on your sensor, and you also want a little bit of light in the room, a little bit of ambient light. You don't want too much. So play around with the light, or alter your sketch a little bit by adding a delay, and it may fix any potential issues you're having scanning your objects. I was going to do a third setup, but it would really make this video too long. I like to keep them usually under 10 minutes, so be sure to check the description for links to those other videos that I'll post shortly. And I'll also post the code to the Facebook page, so be sure to check that out as well. Well, that's all for today. Hopefully you found this useful, and if you did, be sure to like the video by clicking the thumbs up. Also consider subscribing and checking out the Facebook page. The link will be in the description. Also share with somebody else who may find it useful. And I'll see you again very soon with another video.